Imagine you have 2 points on the plane, A with coordinates x0, y0, and B with coordinates x1, y1. What would be the shortest curve, y of x, that connects these 2 points? Obviously, the answer is a line. But how would we prove that mathematically? Well, the first step would be to derive a formula for the length of the curve from A to B. Let's start by zooming into the curve such that it almost looks straight. We see that there is a corresponding dx, dy, and arc length ds. They form a right triangle. By the Pythagorean theorem, ds squared equals dx squared plus dy squared. To get the entire arc length from A to B, we have to integrate all these tiny pieces of ds from x0 to x1. Great, we have an expression for the arc length of a curve y from x0 to x1. This is the value that we want to minimize. But how do we actually do this? Well, in calculus, we learned how to find the minimum of functions by looking at their derivative. Notice what happens to the tangent as it reaches the minimum of this function. The tangent is flat, and the derivative at that minimum is 0. This is important. At a minimum, the derivative of our function will evaluate to 0. Now, let's take a look at our expression for the arc length of a curve. This is a function of our curve y, really a function of a function, which we call a functional. At a minimum, the derivative of this functional will be 0. It helps to look at a family of curves. Let y of x, the blue curve, be the shortest path. Well, in reality, we know this is a line, but for the sake of the proof, assume it's not. Now, y of x plus epsilon eta of x is a curve near y of x. Eta of x can be any function, sine x, log x, 3x, arctan x. Also note that when epsilon goes to 0, the orange curve, our epsilon curve, also goes to our true solution. If we take the arc length of this epsilon curve, using our expression for the arc length we derived earlier, we get the following integral. Now, by taking the derivative at epsilon equals 0 on both sides, switching the derivative and integral sign, evaluating the inside, and noting that at a critical point, the derivative of a minimum is 0, we get the following integral. By performing integration by parts, we can simplify this. Note that eta of x is 0 at x0 and x1 due to our boundary conditions. That means the term disappears. For this integral to be 0, no matter what eta of x we choose, the red part also has to equal 0, namely d dx of y prime x over square root 1 plus y prime x squared. Now, by integrating both sides, we see that it's a constant, which means y prime x is also a constant. We can integrate both sides and see that y of x has to have the form ax plus b. This is the equation of a line. We did it. We've just proven that the shortest path between any 2 points has the equation of a line. Thanks for watching. I hope you enjoyed this video.